So we continue our discussions on operators in occupation number basis. And in the previous lecture, we discussed about single particle operators, which means the operators which actually are just inherited from the Hilbert space of single particle states. So now we will generalize the discussion to multi-particle operators and more general operators. So what do I mean by multi-particle operators? Multi-particle operators means an operator which acts on which non-trivially acts on more than one particle. I mean, this is usually like some sort of an interaction. So, for example, imagine if there is any potential which acts on the both particle. So, if I have such an interaction term, for example, it can be something of the form Coulombic in nature, some Coulombic repulsion between two particles. But notice one thing, that they have no meaning when we were just considering single particles, right? These are inherently some features of multi-particle Hilbert spaces, and we are trying to figure out that. We want to know the occupation number basis. Okay, so in such cases, let's consider situation that operator takes state I1 and I2 and it maps to some state J1 and J2. Okay, so this is some state this is the state of the first particle, this is the state of the second particle, and when it acts on that, it gives me the state J1 for the first particle and state for the second particle. Okay, so then in such a scenario, if I start from an occupation number like this, Then it goes to an occupation number of 2 states increases and occupation number of 2 states decreases. Okay, so it goes in this way. So now in order to do this computation, first we define the matrix element. So it has a matrix element. We define the matrix element in this way. So it basically depends on two states in the bra and 2 states in the ket. And then in this case we have to compute the. So now we want to compute. So this is the matrix element. Now we want to know the action in the product base, in the occupation number basis. Okay, so in order to do that, we compute the non-zero matrix element, which is something of this form. I mean, of course, there are other states. And this is my operator in the multi-particle Hilbert space. Okay, so this is, you remember the construction, for single particle operators we did the construction by tensoring various identity operators. Similarly, there will be a construction like this where this operator will be non-trivial only on two particle slots, and then it for other particles it's just an identity operator, and then you have to sum over all such possibilities. Okay, so that's basically I'm referring to these expressions, but now written in the multi-particle Hilbert space basis. So this computation is done in details in the note, so I will not elaborate on that. But the bottom line is that, so this is equation 1.1.40. But bottom line is that if you do this computation, the end result turns out to be Okay, so this turns out to be the result of this computation which we have presented here. But again, you see this form is very instructive. It has precisely this bosonic enhancement factors. And bottom line is that we can write this operator in the multiparticle Hilbert space in the following way. I mean, again we did the same thing. We did fix I1, I2, J1, J2. If I1, I2, J1, J2 is not fixed, then the computation will be different. But if this, then there is no summation in computation will not be different. There will be just summation, one extra summation. So this thing turns out to be this operator. Okay, so this is more like a two particle operator. In the occupation number basis. Okay, now in this basis we can always define the number operator. The number operator is simply AI dagger AI, and hence the total number is basically sum over the number operators. Sorry, let me denote it R. Okay, now you see one important thing we have done up to this point is that operators that preserve the total number operator, total number of particles. I mean this Ni or Nr individually these things are not conserved, but N is thing. So all the operators commutes. So for example this operator commutes with P. Okay, because it has the number of creation operators and the number of annihilation operators is same in this case. I mean we are not claiming that the occupation in individual state remains constant. So it is not true that in R for all values of R is not true for all R. Okay, so but at least the total number is conserved throughout this for this operator. But you see now once we have this occupation number basis, then we have more freedoms. We can construct more general things. So for example we can construct operators which are roughly, let's say, something like this G, J1, J2, I1, which is like A, J1 dagger, A J2 dagger AI. Okay. So one important thing you notice is that such an operator do not preserve the total number operator. So we denote it at, let's say, U. Okay, so what I'm trying to say is that U dagger is not U dagger, U operator U do not commute with operator N. And since particle number is not conserved, that means that these operators have no these operators cannot be found in the product basis. Because the thing in the product basis is that it always preserves the number of particles. Okay, so it's basically the number of particles on the left hand side on the bra and the number of particles on the kit, they are always same. But in quantum mechanics, the formalism of quantum mechanics does not change the particle number. The formalism of quantum mechanics doesn't allow to change the number of particles. And as a result, anything, any process or any operators that changes the number of particles doesn't have any meaning in terms of the multi-particle Hilbert space in the product basis, because the product basis is more like a quantum mechanical system. We are taking we are just taking a collection of quantum systems, and in that system, in that formalism, it does not allow to change the number of particles. Whereas the occupation number basis can handle such operators very easily. Okay, so this is another reason, that this is another aspect you can see, that in which aspect the particle the occupation number basis is more advantageous, because it allows you to do more robust things which was not allowed for, say, in case of the product basis. Okay. Okay, so this is basically the point we wanted to say about the occupation number basis. And in future you will see that the language of quantum fields the slogan is basically, which we will try to show next time and also throughout the course, is that is formalism of quantum fields. Okay, we will try to discuss next time that what is this, these are objects, how it's related to creation annihilation operator, and then also throughout the course we will see the importance of quantum fields. Okay, so we conclude this session with basically trying to emphasize the fact that the occupation number basis, firstly any operator which is there in the product basis can be written in the occupation number basis. But the converse is not true. In the occupation number basis, there are more general operators which cannot be written in the product basis. And such operators, in that sense, the occupation number basis is more robust. And then we concluded with a slogan which we did not try to justify, is that the natural language to describe the dynamics in the occupation number basis is the formalism of quantum fields.